This is, in some sense, a continuation of what Professor Mukunda presented this morning. And he talked about both the Wigner description in the continuum case and also those in the context of discrete quantum systems. And what we would like to do is now, the two developments have, as you can see, are in isolation. One has a description, phase-space description for the continuum case. Also one has a separate development trying to preserve as many properties of the original Wigner description in the discrete case. It's a completely separate development for which he presented some of the ideas we had been working on, which in some sense, as far as the formalism is concerned, link the continuum with the discrete. Now, in the presentation which I would like to make, we want to go a step further in the sense that we would like to see how one can descend from the continuum to the discrete, not see them as separate developments, but somehow come up with a scheme which allows you to go connect the two descriptions which have hitherto developed separately. Now, I had under the assumption that Professor Mukunda had said that he would need only 30 minutes for his talk. Later on, he came to know that he has 45 minutes. I had included some material as supplement to his talk so that we can fill out the time allocated to us. But he has used up his time, so I will skip. I'll just show some of the details by way of, as in sort of an appendix material to what he presented, and also talk about a little bit about other approaches to discrete Wigner functions, particularly that due to Wuters, and then move on to the main topic which I have, which appears in the title. Which is the one? This is laser. This is the power. So here, just some of the terminology which Professor Mukunda used in his lecture. I have summarized it here, and because I may require referring to these terms later on in my presentation. So Q is the configuration space. In the two examples which Mukunda considered, Q was the real line in the continuum case, and in the other, the discrete case, it was the set of points Zn or Zd. Gamma 0 is what is called the phase space. Sigma is a point in the phase space. Sigma, comma sigma prime is the symplectic product of 2 points on the phase space. Lambda is an isotropic line in gamma 0, that is a line, straight line going through the origin. And then given a lambda, you can define lines parallel to it, and these form a sort of a striation or decomposition of the phase space into a set of set of lines. So this is a decomposition of gamma 0. The lines cover the entire phase space gamma 0. Is this the one? Sorry. This one. Oh, I'm confused. This one?
Yeah. Yeah, this
one. This one. Yeah. Now, some general features of these phase spaces. There are certain groups associated with the phase space, translations, and this is what I would call a symplectic group, which takes an isotropic line to an isotropic line. Correspondingly, there are operators on the Hilbert space. D sigma is the Weyl or displacement operator. Everyone is familiar with it. I am not going to list all its properties. Then we have, these are unitary operators, one for each point in the phase space. Then we have another set of operators indicated by W hat sigma, which are called phase point operators, satisfying the properties that I have indicated here. And these are the ones you take, given any operator like the density operator, you take the trace of W sigma with the density operator, and that gives you the Wigner function. Now, the marginals property, which is an important aspect of the Wigner description, amounts to saying that to each line in the phase space you associate projectors, and that is what translates the marginals property of Wigner functions. That is, if you take the average of the Wigner function along a straight line in the phase space, then what you get is a probability. So these are the basic objects one needs in order to define Wigner functions in the continuum or discrete case. Here, whatever I have done, have written it for the special case of finite state quantum systems, but analogous results can be written down I've done it only for convenience, and analogous results can be applied in the continuum case as well. The relation between the projectors, which encapsulate the marginals property, and the phase point operators, which give us the Wigner function, is summarized in these two lines. That is, you take a point sigma in the phase space and you sum over all the points on you take a line lambda A and you sum the sum of the Wigner phase point operators for all points lying on the line lambda A gives you the projector, and conversely you can solve for the phase point operators in terms of these projectors through this relation. So the projectors and the phase point operators are related in this manner. Professor Mukunda outlined the approach that we have, and that approach is based on first constructing the phase point operators and then imposing the conditions that the phase point operators thus constructed, when added up along, averaged over a line, give you a projector, and that is what, as he pointed out, puts conditions on the signs that appear in the process of taking the square root. Now, I may just mention here that there has been another approach to Wigner functions for discrete spaces, discrete phase spaces, initiated by Gibbons and Wouters. Here, the configuration space is not ZD, but a finite field. And the advantage, in some sense, of using a finite field is that you have all the properties, geometrical properties of lines and points that you have in the context of the real line, because real line is a field and so is this finite field. So you have all the properties like two lines intersect, non-parallel lines intersect only in a single point. This certainly does not apply to the case which was considered by Professor Mukunda, where Q was ZD and you can have two lines intersecting at more than one point and so on. So geometrical properties differ, and therefore the two descriptions are also differ in each other in detail. Also note that when you're talking about finite field, such fields are available only in prime power dimensions. So this approach is restricted to dimensions which are prime powers. Of course, you can reconstruct for any given dimension. You can decompose the number into D into prime powers and use this approach and come up with a Wigner description for arbitrary D. So these are two different approaches to this subject. We would, the square root approach I think is much more general. It does not make any difference whether you're dealing with finite fields or the ring ZD. You can apply it uniformly to all these cases. Now, just to give you a sort of an idea of what this is about, the say for example in the case of a qubit, the phase space looks like this. Then these are what are called decompositions of this phase space into set of parallel lines, 3 of them I have indicated here. And in our approach, for instance, for this problem, we would first consider construct the phase point operators and then require that the sums of phase point operators give rise to rank 1 projectors. In the Booters approach, one would follow the reverse. That is, you would first assign projectors to the lines which are drawn from mutually unbiased bases for reasons that I will not expand on at the moment. So you start with the projectors and use those projectors to construct the phase point operators to complete the description. Needless to say that you can assign projectors to these lines in many different ways, giving rise to many different possible Wigner type of descriptions. The same kind of, in the context of 2 cross 2 space, for example, the same kind of multiplicity of descriptions of Wigner type for even dimensional that arises in our description. So this is just to illustrate the notions and ideas which I have introduced so far. So I will not go into this. This is just for completion, just to show that in the finite dimensional cases, you have many, many possible equally good Wigner descriptions, and I will leave that out. Certain geometric properties of phase spaces based on finite fields. These are the standard properties that one sort of intuitively obvious properties that are inherited from the fact that Q is a finite field. However, they do not remain so in the context when the configuration space is ZD. The coordinates take values 0, 1 to d minus 1. This is an analysis which we needed for understanding our work on making specific calculations in the context of Wigner distributions on ZD, but these details may also be useful in some other context. So here what I have listed is on a ZD cross ZD lattice, on a toroidal lattice, how many straight lines do you have, how many lines pass through a point. This analysis is of course contained in this paper which I have referred here, but they are available, and I'm sure that if someone needs this information in some other context, they are all given in the paper referred here. Now I move on to the main theme, which is a passage from continuous phase spaces to discrete phase spaces. And the motivation for this arose from the context of entanglement in discrete state systems. In the context of continuous variables, through the work of Simon and Duan, Chirac and Sola, one has a complete characterization of bipartite Gaussian states in the continuum. In the discrete case, we have complete results only for the case when you are dealing with the H2 2 cross 2 systems. The idea was, or the basic motivation was, that if I could define a notion of Gaussian states for discrete systems, then could it be that we would have a complete characterization of Gaussians of such states, if one could define them, for the case when the Hilbert space is HD1 D1 cross D2 systems. That was the idea. Of course, one has no general results for D1 cross D2 systems, the idea was that if restricted to Gaussian states, which will be characterized by a finite number of dimensions, much the same way as the Gaussian state in the continuum is described by the variance matrix, could there be a possibility here? So this this requires us to define or come up with a notion of Gaussian states in the context of discrete state systems. Also, you have to keep in mind that after all, somehow in order to translate the ideas that are available in the continuum to the discrete, we have to somehow make sure that our discrete phase space or discrete, the Hilbert space appropriate to the discrete system somehow sits in the continuum. And I will now sort of outline some of the ideas which are a part of the work, ongoing work in progress with Marcus Appleby, Mukunda Simon, and so on. And also, yeah, I will also remark that here that because the finite field, this process of descent from the continuum to the discrete, of course, would naturally exclude the Wooter's type description, because the finite field Fd does not sit in any natural way in the real field, whereas the ring Zd sits naturally in R. So whatever I have to say will apply to the descent from the continuum to the case which was considered earlier in Mukunda's work. All right, so the idea here is that in the continuum, if you take two displacement operators and you find that these two displacement operators commute with each other, provided the symplectic product between the 2 points sigma and sigma prime is a multiple of 2 pi, where d, so it's minus 2 pi d, where d is an integer. So now suppose I take two such points, let me call them sigma 0 and sigma 0 prime, such that their symplectic product is minus 2 pi d. Then these two displacement operators would commute with each other, and you can find simultaneous eigenstates of these operators corresponding to, say, the eigenvalue 1. Of course, the eigenvalues are just phases. You find the simultaneous eigenvectors of these corresponding to the eigenvalue 1. This turns out to be the expression given here, which involves, so these are what I would call the position states in the context of discrete variables, taking values 0 to d minus 1, and these are the position continuum, the eigenstates of the position operator sampled at these points. So this is the, so to summarize, you take two displacement operators such that they commute with each other, and the sigma prime is minus 2 pi d. You find out that the simultaneous eigenspace of these commuting operators is d-dimensional, and these are the eigenvectors. Now I have to move quickly. Similarly, you can also construct these eigenstates in the momentum basis. Of course, now if you calculate the scalar products of these eigenstates, they would involve Dirac delta functions, because by virtue of the fact that these states here are the eigenstates of the position operator in the continuum. In order to alleviate this problem, we find what we would like is a discrete phase space in which these states form an orthonormal set. So to alleviate this problem, we do a minimal modification to the scalar product in the continuum, which can be written in terms of coherent states in this form to the scalar product that is given here. So now all you do is this scalar product involves integration over the entire complex plane, but you now restrict yourself to the parallelogram generated by the sigma 0 and sigma 0 prime, which I had indicated earlier. You find that with respect to this scalar product, the states that we had constructed form an orthonormal set, which is what we needed. And not only that, you also find that the overlap between the coordinate and the momentum eigenstates is given by by 2 pi I d, or that is to say the momentum and the coordinate states are related to each other through a finite Fourier transform. So exactly the kind of structure that you need to describe the state space of a d-dimensional discrete system. So now I will try to, so this also allows us, gives us a procedure to link the continuum with the discrete. I will illustrate it through a simple example. As I have said earlier, that some of these ideas are still in the process of being put on a firm mathematical footing, but I will simply illustrate what the approach is in order to link the continuum with the discrete. So let's consider, for example, the coherent state which is described in the continuum, whose position wave function is given here. This is a Gaussian. I would like to see how does this translate when to this d-dimensional subspace. So now what I do is I take the overlap of this state with the states that I've constructed, and this is given here. Now you QP, of course, take values in a discrete lattice. So I've introduced this alpha and beta, which are integers, and this is then the overlap expression for kz, and which can be written in terms of Jacobi theta functions in this form. So this is then, in some sense, the representation or the image of the coherent state defined in the continuum restricted to a d-dimensional subspace. Now, what one can do is to look at how good is this, what is the connection between the continuum and the phase space so defined on a d-dimensional lattice. And I have just given here plots of the for the case when z is 0, which corresponds to the ground state of the harmonic oscillator for values d, 3, 5, and 7. The envelope is the full Gaussian, and you find here that if you evaluate the theta function and compare it with the Gaussian in the continuum, even for d equal to 5, the agreement is perfect almost. And so this would then be this would mean is that this is the discrete analog of the coherent state for a d-dimensional quantum system. You can also then consider other possibilities like a squeezed vacuum. I've just given you here the graphs of in that context, and again you find that d equal to 5 onwards, the agreement with the Gaussian distribution is perfect. And I've chosen this particular state because, as you all know, the Gaussian state, Z is a Gaussian state meaning that its Wigner function or any other phase space functions is a Gaussian. I've chosen that as an analog, and in order, because what I'm doing is basically looking for analogs of Gaussian states in the discrete context. Also, these theta functions have the nice property that their discrete Fourier transform is also a theta function, much the same way as the Fourier transform of a Gaussian is another Gaussian. And you also find that the relationship between the widths of these two distributions also follows the same pattern as it does in the continuum. Here I've given you graphs of for the in the momentum space, and so to summarize, we have presented at the moment a heuristic scheme for passing from the continuum to the discrete. If successful, the scheme would enable us to translate structures available in the continuum, in particular the notion of Gaussian states, to those in the discrete and vice versa. Whether the original motivation of this would be fulfilled or not remains to be seen. This would require us to study properties of multivariate generalizations of theta functions if they exist, and forms, and this will keep us occupied in our advancing years, because all the participants in this effort are over 60, and we can be fruitfully occupied with this investigation for the rest of our lives. I've taken 5 minutes more, I'm sorry. Yes. Thank you very much.
Questions? So can you define some kind of analog of the Hudson theorem here? I mean, suppose you have a Wigner function with suppose you have a Wigner function with only positive quasi-probabilities.
Yes.
So then can you represent it in terms of these Gaussian states that you have found?
For this actually has been already the square analog of Hudson's theorem in the context of discrete systems has already been done. And what's his name? No, this is a big problem. David Coase, he has done this work, and this is was actually contained in his diploma thesis, analog of Hudson's theorem for the discrete case.
Those states are the so-called stabilizer states.
That's correct.
So are these states the same, stabilizer states are the same as the states, Gaussian states that you are forming here?
No, not these. So I think that is another, these are not the Gaussians. In the continuum, what he showed was the states that appear in the Hudson's theorem, or the Gaussian states, but these states, I think there is a difference. This notion of Gaussian states can be, that we have defined, is by appealing to a Gaussian, which a notion of a Gaussian is available only in the continuum, and we are trying to see what is the analog of that in the discrete context.
Do you have any operational interpretation in mind when you are forming these Gaussian states? Because stabilizer states already have, non-stabilizer states have an operational interpretation in terms of being useful as an ancilla for computation.
Yes.
So do you have any operational interpretation in mind for non-Gaussian states?
You see, this is still some work in nascency. We're still in the process of completing. I have just given you some simple examples to show what a state in the continuum, like the ground state of a harmonic oscillator, looks in this language. There's still certain things to be worked out, to be put on a finer, firmer mathematical grounds. I think it's a bit too early for me to be able to answer these questions.
We can talk later, thanks.
Thank you, both of you actually, for these informative talks. I have a question which I wanted to ask Chaturvedi, Mukunda, as well as Simon, who is not here. But since two of you are here, the question is, the original motivations for the Wigner function include the fact that positive Wigner functions might give a sort of classical distribution for quantum states. Now, recently, several theory papers as well as experimental papers have shown that states which have positive definite Wigner functions nevertheless violate Bell inequalities involving pseudo-spin operators. If you could, either of you, give any comments on this, it might be useful for the future. The experimental demonstration and the theoretical demonstration are for the two-mode squeeze states, which is continuum, but there will be probably analogs in the discrete case. Because these motivations about marginals are common in the thing that Subhash and you described as in the continuum case. So if it is possible to give some comments which suggest future work, that would be useful.
I can only answer you partially. In the continuous case, all our work tries to keep very close connection to the symplectic groups, because they are the linear canonical transformations preserving the canonical commutation relation. We would like to define Wigner functions in such a way that they transform as simply as possible, covariantly, under those groups, under the linear symplectic groups. Whether that can be maintained in the discrete case is still to be seen. Subhash has told you a little bit about the use of discrete symplectic groups in the list of all isotropic lines and so on. But I think those groups play an important role in our thinking. You might have something in place of the Wigner function in which the symplectic group has no real role to play. For example, mod psi of q squared times mod phi of p squared is a phase space distribution, gives you two marginals, but it is very unnatural as far as the symplectic group is concerned. That's all I can say.
That's not quantum mechanically, it's not defined by one, how should I say? Marginals are naturally defined by expectation values of quantum operators. But what you said has connections to more general descriptions. So anyway, the general question which probably the future can address is that quantum mechanics, of course, is well defined, either in terms of density operator or in terms of the Wigner function. But is there any analog of the Wigner function, perhaps some extension, whose positivity will signal classicality? That is not clear to me.
Yep. Suppose I think I had asked this question to you earlier. You know, this von Neumann's proof of completeness of the coherent state. You know, that also involved, you know, these kind of theta functions because it was on a lattice.
Yes.
Does it have any relevance to?
No, that is a question posed in the context of completeness of coherent states, and whether you restrict yourself to the von Neumann lattice, there they appear in a natural way. But I do not think that the two are related, because here this involves, I think they are.
We will discuss, yeah.
Great, let's thank the speaker again.